Okay, so the second question is my column isn't working properly anymore. What should I do? Again, it's a very general question, and there are a few ways in which we can tackle it, and we'll look at 5 ways that columns can fail. This is out of a Snyder and Kirkland book, Practical HPLC Method Development. They touch on these 5 topics, and we will talk about those here today as well, specific to our chiral columns. Although this book was written for chiral or for chromatography columns in general, the answers to these questions are the same, whether it be for chiral columns or for achiral columns in this particular scenario. So the first one we'll touch on is either a partially or a fully blocked frit or column bed. Second would be impurities adsorbed onto the column. Third, a poorly packed column, which we're not going to address in this presentation only because the technology for packing columns has advanced quite significantly since the book was originally published. That's not to say that a column can't be packed poorly, but the consistency in which columns are packed now, especially our columns, we QC them before they leave our facility. They have to meet a spec before they leave. So this is generally not something that is an issue. The other 4 are. So we just won't address it in this presentation today. Fourth, void formation from shock, whether it be thermal shock or equilibration shock. And then chemical attack is the last one. So let's look first at blocked inlet frits. Blocked inlet frits can be as a result of either poor sample cleanup or some insolubility of, say, the sample coming in contact with the mobile phase. And generally speaking, it will manifest itself usually in a pressure increase, but it will also manifest itself in split peaks. Up top, scenario A here is a split peak sample of kind of an actual crude sample, B being for an analytical standard, so it's nice and clean, but the same concept, it's split peaks. It might also manifest itself in peak tailing or what could be a more pronounced shoulder on the backside of the main peak. And so if you look at what exactly is going on within the structure of the column, it makes pretty good sense that you'd see it manifesting itself in this way. Under normal conditions, you have a uniform flow across the inlet frit, and so your analyte passing through should be coming through in a normal flow. But if you have some material on the inlet frit which is causing this disturbed flow, you will have then a second path and therefore a second peak of sorts that's coming through. So it could be as dramatic as a split peak, or it could be less dramatic in a tailing or as a shoulder. Here are a few pictures of what blocked inlet frits could potentially look like. On the left-hand side is a really, really bad blocked inlet frit. Obviously, the frit should be kind of nice and white and clean. This has some really earwaxy, brown, yellow looking material on it. But it doesn't need to be this dramatic to see an effect. This is a second example here where you have a clean inlet frit here on the right. Just this little bit of insoluble material here in the center was enough to begin disturbing the flow. This column saw slight increase in pressure and it began to see some peak doubling. So it can happen pretty quick, unfortunately, if the sample is not cleaned up well. The second scenario of the adsorbed impurities onto the column, this can happen again from poor sample cleanup, but is particularly prevalent when you're injecting biological samples, botanical samples, or other extracted samples. Obviously, in real world applications, it's not always feasible to have a nice, clean analytical standard that's going on to the column, but you do have to realize that if it's not a clean or a junky sample, there is a possibility that that material could stick to the column. And so this is an example of what that looks like. This is a 2 centimeter prep column here. It's a silica gel chiral stationary phase, so it should be a nice white powder. This is obviously not a nice white powder anymore. And so this is a column that would need some work in order for it to be recovered. Void formation, either from shock from pore equilibration or from thermal shock. This is a bent inlet frit on a 5 centimeter prep column. This was an SFC column, and it resulted from, you can kind of see it here, some material being gathered on the inlet frit, so a clogged inlet frit, and then the pressure being increased too quickly, too high, and ended up bending the inlet frit. But in doing that, it actually formed a void in the head of the column. And so you now had all of these extra spaces in which analyte could come through in different ways. This scenario will actually show peak fronting as opposed to peak tailing, because everything will be flying through the column relatively quickly. But void formation is definitely an issue if you are cramming things onto the column at too high of a flow rate or too high of a pressure. This is another example where the inlet frit bent in to the column bed, and then the customer actually flipped the column and ran it in the opposite direction. So what happened was, you can see here, some cracks formed at the seal, and in running it backwards, they actually pushed the CSP out of the inlet, and they ended up losing what you can see here, something like 30 to 50 grams of chiral stationary phase. So this could have been avoided, obviously not flowing the column at too high of a flow rate, but also making sure that the inlet frit didn't get clogged with sample they were using. In this case, a mismatch. They were putting on a sample that was dissolved in dichloro or DMSO, and it was hitting a methanol solution, which it was not very soluble in. So material crashed out, bent the inlet frit, and then the problem just compounded on itself. And then the last scenario mentioned was chemical attack. So these chiral stationary phases, even the immobilized chiral stationary phases, are, you have to remember, silica gel based. So there are some limitations or some restrictions you have to be concerned about. So making sure that you develop methods that have a pH that are higher than 2 or a pH that's lower than 8. In the case of using a buffer like phosphate, definitely it needs to be lower than 8. If you're using something a little milder on the column, a formate or bicarbonate buffer, you can go up to pH 9, but obviously the closer you get to that threshold, the more likely you are to damage the column long-term should there be some variation or something like that. Avoid using harsh additives like hydrochloric acid or harsh basic additives like sodium hydroxide. We've done other seminars on what method development looks like, and our preferred additives for acidic compounds is either TFA, formic acid, or acetic acid. They are fairly easy on the column at less than 0.5% by volume. For preferred bases, we're usually using either diethylamine or triethylamine if we're under normal phase, polar organic, or extended range conditions. We can't use those bases though under reversed phase conditions, because it will result in a pH of the mobile phase that's too high. So we either use the buffered phosphate or buffered bicarbonate systems instead. And then making sure that you're not using incompatible solvents with especially the coated phases. The immobilized columns can withstand things like dichloromethane, ethyl acetate, DMSO. Those are restricted solvents though for coated chiral stationary phases. Even a little bit of these solvents left over within the system, say just a few microliters, can damage the coated CSP. So make sure if you are using one system for all of these different mobile phases that you flush the system out well. Make sure that you're flushing all the lines with ethanol first. Make sure that your samples that you're using don't contain any of these forbidden solvents when you're using them on coated chiral stationary phases. Even, again, just a few microliters of ethyl acetate or DCM left over in a sample can, over time especially, damage a coated chiral stationary phase. So that doesn't really answer the question yet. Those are a few scenarios as to what can cause a column not to work. So my column is not working, how can I fix it? Well, preventative measures in this case actually are the most important thing, especially when we look at the clogged inlet frits and the material adsorbed onto the column. So make sure that you're implementing good sample cleanup. That is going to be dependent upon your scenario, but it could just be something as simple as using a solid phase extraction cartridge to get rid of some botanical or biological material that shouldn't be going on the column. It could mean using, a sacrificial achiral column first, running things through just a silica column or a C18 column to try to remove some of those other impurities that might eventually, over time, clog the chiral column. And of course, the use of a guard column is always recommended, guard columns being considerably less expensive than the corresponding analytical or preparative column can save you money and save you hassle in accidentally wrecking that more pricey investment. So using a guard column just to make sure that things are caught before they head on to the main column. Ensuring that you have mobile phase and sample solvent match. I talked about those prep columns that were damaged as a result of customer using a DMSO solution for sample prep and then putting it into a methanol solution for the actual mobile phase. If you have to do that or you choose to do that, you do take the risk of material crashing out either at the head of the column or on the column itself, and that will eventually build up and cause either the inlet frit to clog or peak doubling, peak splitting, all of those things that I previously mentioned. So make sure that the mobile phase and sample solvent are matched at least as closely as you can get them. Ideally, they should be the same. Proper column equilibration, especially for these larger prep columns. The surface area of the inlet frit is much larger than that of the analytical columns. And so if you go from atmospheric pressure to 400 bar on an SFC column, there is a pretty good chance that you're going to bend the inlet frit. So make sure that if you are going to those higher flow rates or those higher pressures, that you do a gradual column equilibration. You don't just throw the system on and have it go right up to operating pressure. Same goes with changing mobile phases as well. If you're going from, say, 100% aqueous to organic, you probably want to have a nice slow equilibration as opposed to a really rapid change in percentage. And then column regeneration is an option for immobilized chiral pack columns only. Some of those scenarios where there's material that's crashed out on the column itself could very well be more soluble in something like dichloromethane or ethyl acetate. So you can actually wash the column with those harsher solvents if it's the immobilized columns that you're looking at, and potentially solubilize the material out and kind of restore the column. So this is an option for those. And if you are experiencing some column history, some column memory, which is a phenomenon that exists for all polysaccharide chiral stationary phases, this is an option as well to potentially kind of reset, as it were, the performance of the column.